Lesson 21, Activities. In July 2000, Massachusetts population was given there, and in 2007, population is a little bit bigger. Let's assume an exponential growth model and write an equation that models the population T years after July 2000. Okay, so I'm going to translate these two pieces of information into two ordered pairs. So it says T years after July 2000, so that means that the first point is 0, comma, and then the first number. And then the second point is 7 years later, so that's going to be a 7, comma, and then the other population number. Okay, and we've already seen how to get and the equation of an exponential function that goes through 2 points. So you got two choices here. You could either do the P of t equals P sub 0 a to the t, or you could do P of t equals P sub 0 e to the kt. Makes absolutely no difference which one you do, but I'm not going to do both here. I'll just do the first one. So plugging into the first one, the first point, 0, and then the 6,300,000 number, the left-hand side becomes the 6,300,000 number. And the right-hand side becomes P sub 0, which we don't know, A, which we don't know, to the T, which is 0 for that first ordered pair. Okay, and then the same deal with the other equation. So the left-hand side becomes the 6,400,000 number. And the right-hand side is, again, P0 times A to the, in this case, T is 7. Okay, this first equation is nice because A to the 0 is 1 for any value of A. So that tells me that P0 is this first population number, which of course makes sense, right? Like if we're starting the clock in July 2000, then yeah, this 6,300,000 number is the initial population, and that's what P sub 0 stands for. So that means that we can take, let's do this here in a different color. We can take this 6,300,000 number and plug it into the other equation. So copying the left-hand side equals, and now P0 becomes the 6,300,000 number times A to the 7. And great, now I've got an equation with just one unknown in it, A. So we're going to divide both sides by the 6,300,000 number. And we'll get a decimal here, but we'll try to keep this number stored on the calculator. So this is not A, this is going to be A to the 7. Okay, so here we go. I'm actually going to type these numbers in individually and store them as A and B. Okay, so 6, 3, 6, 2, 5, 8, 3. Let's store that as A. And then the other number, 6, 4, 6, 7, 9, 1, 5. And we'll store that as B. Okay, let's pause, make sure we got them typed correctly. Okay, that looks good to me. And so this is the B number divided by the A number. That's the A to the 7th. So alpha B divided by alpha A. And so we're going to put that number right here for our A to the 7th. So about 1.016. When does it say? Nearest, round to the nearest 100,000. Okay, let's count 100,000. So that's tenths, hundredths, thousandths, 10,000ths, 100,000ths is that 5, and it stays a 5 just barely. But we're going to leave this unrounded number on the calculator, 1.01655. And that's A to the 7th. So in order to find the value of A, we just take the 7th root of that number. Okay, that looks good. So we're going to raise this to the 1/7. That's the easiest way to think about doing the 7th root, to the 1/7. Okay, so that's our value of A. Let's go ahead and store that one. So we're going to call this one C. Store this as alpha C. Okay, so to the nearest 10,000th, 10th, 100,000, 10,000, 100,000, I think we're supposed to go to. So that's the 4, but the 4 gets rounded up to an 8, right? 10, 100,000, 10, 100,000. Okay, 1.00235. 1.00235. So that means that our formula, when all is said and done, see if we can squeeze it in here. P of t equals, so we found P sub 0 is just the 6,300,000 number. Come on. Okay, so 6,362,583 times a to the t, and we just figured out a is roughly this 1.00235 raised to the t. Not a lot of room there, but that is our final answer. That's our formula for the population. Then it says use the population to predict, use the model to predict the population in July 2008. So remember, t equals 0 is the year 2000. So this is really just asking for p of 8. And so we're just going to type p of 8 onto the calculator here. And we can do that pretty easily, I think. So we called this number a and this number c. So it is simply a times c to the 8th power. And this is why I wanted to store the numbers a, b, and c, is so that we wouldn't have to type them over and over again. Okay, so 6483104. All right, so that's our prediction for the population in July 2008. Then it says the actual population was 6,497,967, and we're going to find the percent error. So here we go. Percent error equals, all right, so we take the, I always forget whether it's like the actual number minus our estimate or the other way. So I think, let's see, so are we too high or too low? So our estimate is 6,483,000, and the right answer was 6,497,000. So we are too low, and I know that that means that our percent error should be a negative number. We were under the right answer. And so to get a negative number, we need to do the estimate minus the actual, and then we divide that by actual. And then to make it a percentage, you can multiply by 100. So that was my way of just remembering or figuring out whether it's estimate minus actual or actual minus estimate. Okay, so we will do our subtraction here. So our estimate was 6483104, and we subtract off the right answer, 6,497,967. We divide by the right answer, multiply by 100, and we will get our percent error over here. Okay, so this number right here, I know we're storing a lot of things, but I just don't feel like typing them all out. So that one is going to be D. That is our estimate. Hey, how about E for estimate? We'll do something intelligent instead of just going in order. Okay, E is the estimate. The actual number right there is the 6,497,967. Make sure I got that right. 6,497,967. Good. So that's the actual answer. I'm going to store that one as D. Great, and so this formula is really E minus D over D. Super, easy to type in. E minus D over D. And then we'll multiply by 100 to get a nice percentage. So we were off by less than 1%, only off by about 0.2%, which is pretty darn good. So we'll say 0.229. Negative 0.229%, not 22.9%, but 0.229%. Okay, when will the population reach 7 million? So again, we're going back to our red circled equation there, and the left-hand side is our 7 million. So 7 million equal to, and then I'm just copying the right-hand side. And we're trying to solve this equation for t, and wouldn't you know it, the variable is in the exponent, so I know that logs are going to be the tool of choice. But before we take the log of both sides, we need to get the exponential piece by itself, which means that this number needs to go to the other side, and we move it to the other side by dividing. So we'll do 7 million divided by the 6,3 and change. So that's equal to 1.00, I'm going to put some space here, 1.00235 to the t. and we're going to type that left-hand side onto the calculator in just a moment, but I know that the right tool here is logs, so let's do the log of both sides. I'll choose ln. You could choose common log or log with any base. And then I'm really going to save some time here and say that that t on the right-hand side, we know we can move it into the front. That's our property about log of something to a power. And so then I think I'm ready to just write down our final answer here. So the final answer is going to be on the right-hand side. So we're going to divide both sides by ln of 1.00235. So the right-hand side is simply t. I'm actually going to swap it over to the left-hand side. And so it is ln of the fraction divided by ln of 1.00235. Okay, and so we'll get a decimal here. But again, lots of numbers there, so if I can just remember which ones are which, then I can type this in very easily. Okay, so we called the first population number A, and that one is right there. So we're going to divide by A. The second population number was B. I don't need that one, but I'm pretty sure that means that we called this 1.00235A. And so we're going to divide by ln of A. And if you're just not sure, like what you defined, you can just very quickly say, hey, what was, I think I just said A, but this is the C number right here. And so that's the A number, and then we'll just verify that the C number is the 1.00235. Super. So I think we're ready to go here. So ln of, 7 million, this will be real fancy. This EE means times 10 to the, and there's 6 spots, 6 zeros here. So there's 7 million divided by, and then we said this was the number A, alpha A, and then divided by ln of C. So again, a very efficient way to use the storing of numbers on the calculator. So it looks like it takes about 40 years. We'll call it 40.7. Okay, and then finally, calculate the doubling time for the population. So the doubling time is how long it takes for the population to double. And so I'm gonna, what am I gonna do? Let's take a look at this red circled equation again. I want the population to be double what it initially started at, and this is what it initially started at. So I should double that number and put it here. But I'm just gonna write that in a different way because I don't feel like writing that 6 million number again. So instead, I'm gonna say the right-hand side of that equation is p sub 0 times 1.00235 raised to the t, where p sub 0 is the initial population, and if p sub 0 is the initial population, then double it would be 2 times p sub 0. So this avoids the having to write down that 6,300,000 number, and then if I just divide both sides by the p sub 0, then we get 2 equals 1.00235 to the t. Again, there was no need to write that the 6,300,000 number. Okay, the variable's in the exponent, so logs are the tool of choice. So we're going to do ln of, let's do common log this time. Change it up. Who says we can't be wild and crazy? So this is log of 2 equals, and then the log on the right-hand side, 1.00235 to the t. But again, our favorite property of logs is that log of something to a power, that power can get picked up and go right down into the front. And so then our final answer here is t equals, so divide both sides by log of 1.00235. So we get the log of 2 divided by log of 1.00235. And then we will type this onto the calculator. It's making a big old mess over here. So this time we did common log. So we go log of 2 divided by log of, and then again, this number was our C. So just log of C. And so the doubling time is just under 300 years. 295.5 years. That's how long it would take the population of Greenfield to double according to this model. Okay, number 2. So the graph of this function y equals ln of x is given. And we're trying to sketch the graph of y prime on the same set of axes. So we'll just do our standard pick a few points and then draw some tangent lines and then estimate the slopes of those tangent lines. So ultimately, again, on the graph of the derivative, y prime is what we're looking to graph. The points are of this form, x, and then the slope of the tangent line at that x. So we'll just pick a few. How about we go purple here? All right, how about we pick this point here at 2, and we'll pick one at 8, and then maybe another one at 16, and then how about one more way over here at 28? And then why don't we pick one that's like way over here as well? How about this guy? Okay, so drawing little tangent lines at each of those points. I'm going to be more precise here because we're trying to estimate slopes of lines. So I'm going to pause and use my line tool here. You can use a straight edge. You should use a straight edge. Ultimately, we're going to be trying to count boxes. So I'm going to make these lines a little bit longer. Okay, so I've drawn 1, 2, 3, 4 tangent lines. I'm actually not even going to bother with the last point because it is so similar to the second to last tangent line. I'm going to have a hard time counting boxes anymore or distinguishing those two lines from each other. So let's count boxes on this first tangent line, the left-hand one right here. So just looking for nice points that I can read off the grid. Perhaps this one right here looks like 4, 8. And then another nice point. Do we see any other nice points? Oh, maybe this one down here. I think that's roughly -2, -6. So you could count boxes on here, but only because the scale is the same. And so you should be careful about just counting boxes. Like if you really want to do this right, you say the change in y is from 8 to -6. That's a 14. So what are we doing here? Let's do this one. So it's a change in y, 14 over, and then the change in x. So we go from -2 over to +4. So that's a change of 6. And so 14 divided by 6 is 7 divided by 3, and that's roughly 2.3. Okay, and then the same deal for each of the other lines. So on the next tangent line, looking for nice points. I see 2 that are kind of close to each other. We'll grab those 2 there. So the slope of that one, roughly, so the change in y here goes from 6 to 4, that's a 2, and the change in x is a 4 from 12 down to 8, so looks like that's about a half. And then the next one we'll do in blue, so looking for nice points on the next line. I guess I see one right there. It looks like 22, 4. And I don't know if I'm going to find another one. Maybe I'll just grab the one that's at 8. It's not exactly at 2, but it's probably close enough. Okay, so then the change in y here, going from 2 up to 4, that's a 2. So the slope here is roughly 2 over. And then the change in x, going from 8 all the way over to 22, what is that, 14? I think that's good, 14. And then 2/14 is a 1/7. Running into my other work here. Okay, we're going to move this thing out of the way. M is roughly 2/14, which has a decimal, maybe 0.1 something. Okay, so 0.14, we'll say. Okay, and then the last one might be even tougher to pin down. Looking for nice points on this tangent line. Guess maybe this one over here at it's at 30. Guess that's at 32. Maybe it doesn't quite get to the end of that box. I don't know. And then another nice point on this one, I'm having a hard time finding anything with coordinates that are easy to read. I'm going to pick this one and say, just call that 16, 2, which it clearly isn't. Maybe it's a little bit bigger, like 16 and then 2.5, 16 and 3. Let's call it 16 and 3. Okay, so then the change in y, if it's going from 32, change in y going from 3 Going from 4 to 3, that looks like a change in y of 1. And then going from roughly 32 to roughly 16, that's a 16. Okay, the slope there is roughly 1/16. And we'll get a decimal, and then we're just going to plot these points on the derivative. 0.06, very close to 0. Okay, so again, plotting points of the form x and then slope. Okay, so we'll do this in red. No, let's do this in black. Okay, so the first x looks like it's, I don't know, point, I'm looking at this point right here, so maybe that's like 0.2-ish. And then the slope we said was around 2.3. So I just go to that same x and I go up to roughly 2.3. I don't like black there because the tangent lines are black. So let's do purple. Okay, so we're going to that same x and then up to about 2.3, roughly here. And then the next x is around 2, and the slope of that one in orange over there is 1/2. So 2.5. It's actually not far from where that point really is. I'm going to try moving that up just a little bit so that I have some space. So those points there. And then at 8, we've got roughly 0.14, just barely above. I'm exaggerating. It's not that far above the x-axis. And then finally, this last point at 16, the slope was around 0.06. So that's basically on the x-axis, but it's actually just a tiny bit above. And so then we've got this curve, which is going to connect these points and get really close to, but not quite touch. And in fact, as we keep going closer, if we follow the original curve, it's hard to see now because it's a big old mess, but this curve gets very, very steep. In fact, almost vertical. So what does that mean as I follow my derivative curve to the left? It means that it actually goes up and grows without bound. It never touches the y-axis, but it does have a vertical asymptote of the y-axis. Okay, so then there's my graph, my rough sketch of the derivative of ln of x. Does it look like a familiar function? I'm hoping it does. You can pause the video if you haven't thought about it, but I will put a question mark here. So pause the video, come back after you've had a chance to think. Maybe, just maybe, that's the graph, or part of the graph of y equals 1 over x. Okay, number 3. The amount of a sample of 50 milligrams of radioactive material, which will remain after T half-lives have passed, is given by this formula. So let's explain what the inverse represents, and then we'll find the equation for the inverse function. So for me, what I like to do is think about the original function and write down its input and its output. So the input in this case is the value of T, which is the number of half-lives. So the input for this original function is number of half-lives. And then the output for this original function is the number of milligrams that remain. So I'm just thinking about the units for the input and the output. And therefore, for Q inverse, the inverse function, which we symbolize with a -1, has inputs and outputs that are swapped, right? And so the input here is the number of milligrams. And then the output is the number of half-lives. And so if I wanted to write a sentence about what the Q inverse function represents in this real-world situation, I would start by saying, well, its input is the number of milligrams remaining, and the output is the number of half-lives it takes to get there. And so I can just write that, maybe in slightly nicer language. Q inverse takes a given amount of radioactive material in milligrams remaining and outputs the number of half-lives it takes to get there. Now this sentence is different from the way the sentence looks in the answer key. So go ahead and take a look at the answer in the answer key. And if you like that format better than this one, then by all means, go for it. They're both full credit answers as far as I'm concerned. On the rest of this page, I'm actually not going to write down the stuff that I just wrote down. I'm not going to write the interpretation sentence. You can just follow the format here if you like this one, or compare your answer to the answer key if you prefer that form. But what I am going to do in this video for all the ones on this page is part B, which is to find the equation of the inverse function. Now there is a hint here that says that, or a suggestion that says that because these variables represent real world quantities, we're actually not going to do the step where we swap the x and the y. We're not going to swap the q and the t. We're just going to solve for the independent variable. We're going to take the original equation. So I'm putting this one up here now. We'll take q equals 50 times 0.5 to the t. And we're just going to solve for t. And then we're going to stop the problem right there when we solve for t. So the variable t is in the exponent, so logs are what we're going to use. But first we need to get the exponential piece by itself. So that 50 needs to move to the other side. So we divide both sides by 50. And then the variable is in the exponent, so we'll take the log. I'll do a natural log of both sides. And then the left-hand side stays as it is. But the right-hand side, we're going to bring that t down in front of the log. And then we're going to divide both sides by 0.5. And that's it. That is our formula for the inverse function. It's a t equals, and q is now the independent variable, the input variable. So if you tell me a value of q, how many milligrams you want, then plug that into this formula, and the formula will tell you the value of t, how many half-lives it will take to get there. In the answer key, it writes this as f inverse of q, but it's still a t at the end of the day. Okay, so number 4, like I said, not going to do the interpretation. I'm just going to do the solving for the inverse function. So we are going to solve the equation. I'll write it without the f of t in the middle. But we're going to solve this equation right here for the value of little t, the input variable. K is a constant. So again, logs are the right tool because the variable is in the exponent, but the 5 needs to move, and the 95, and they have to go in the right order. So clearly the 5 goes first by subtracting. And then the 95 goes next by division. And then we're going to do the log of both sides. Clearly, natural log is the choice here because the right-hand side is e to some stuff. So I'm just copying this here and putting a little space. And in that space, we're going to take ln of both sides. The left-hand side is just copied. Right-hand side, you could bring the negative kt down in the front. That's what we've been doing at this step, right? The power inside of a log can come in the front. But let's take advantage of the fact that ln and e are inverses. And we know ln of e to some stuff is just the stuff. And so literally the ln and the e cancel, and you just get negative kt. Nothing wrong with bringing the negative kt down. You'd be left with ln of e, which of course is 1. So we're just skipping that one step. And then we'll divide both sides by k, negative k. Remember, we're trying to get t by itself. So ln of t minus 5 over 95 divided by negative k is equal to, so it's equal to little t, and we could also call it f inverse of capital T. So the inverse function of the capital T function. And I know I said I wasn't going to write a sentence, and I'm not going to, but if you like the input-output idea, you can actually hold off on thinking about it until you get here. The input clearly is capital T, which is the, what is it? The temperature, and the output is little t. So apparently, if we give this function the temperature that we want the cup of water to be, and we plug into this formula, then the output will be little t, how long it takes to get to a given temperature. Okay, number 5. We're going to solve this equation for capital I. I'll rewrite it without the f of I in the middle. I sub 0 is a constant. Okay, so let's go ahead and get the log piece by itself. So this is the first time where we're going to be undoing a log. Well, we want to get the log piece by itself first by dividing both sides by 10. Okay, so how do we get rid of that log? Because right now the variable that we want is I, and it's trapped inside of a log. So we're not taking the log of both sides. Somebody has already taken log of both sides and got us this equation. So how do we go backwards? Well, we just go to the definition of log. Remember, the common log is an implied base of 10, right down here. I'll put parentheses around this. This is the one thing inside of the log. And then our basic arrow pattern was translating a log equation into its corresponding exponential, was to take the base, raise it to whatever's over there, make it equal whatever's in here. And so that's all we're doing. 10 to the b over 10 equals, and then the log isn't here anymore, it's just I over I sub 0. Okay, that is the definition of common log. We're just translating it to its corresponding exponential version. Okay, and again, solving for capital I, so we just have to multiply both sides by the constant I sub 0. And so it's I equals I sub 0 times 10 to the b over 10. And if you wanted to, you could call this F inverse of b. So again, interpreting this one, the input is b and the output is capital I. So if you tell this function the loudness of a sound, that's the b, then this function will spit out the corresponding intensity. Given a loudness, the function will find the corresponding intensity of that sound. Okay, and then the last one, number 6, a logistic model is that A, B, C are constants, and we're trying to solve for little t. Let's give it a shot. P equals C over 1 plus A e to the negative bt. Okay, trying to solve this equation for little t. So first, I don't like that it's a big fraction, so I'm going to multiply both sides by 1 plus A e to the negative bt equals C. I'm going to highlight here in green. The thing we're trying to solve for is t. That's the goal, is get everything away from that. So now it is currently here. At least it's not in a denominator anymore. So two choices. You could either multiply everything, you could distribute the p through, or you could just move the p to the other side by dividing both sides by p. I'm just going to take a quick peek at the answer key. Oh, it's got both. So I'm going to go ahead and distribute, but totally fine to divide both sides by p. So distribute the p. P plus a p e to the negative bt equals c. And again, trying to solve for little t right there. So now let's start moving everything away from little t. So the p needs to move, that a and p need to move, and then we'll have the e part by itself. So that's the next sub-goal, is to get the exponential piece by itself. So we'll subtract the p from both sides. So c minus p, and then we'll divide both sides by ap. And now the exponential piece is by itself. So now we're going to do ln of both sides. Again, using ln specifically here because there's an e. So I'll copy both sides but leave a little bit of space. So ln of both sides. And now on the left-hand side, good things happen. The ln and e cancel, so we just get negative bt equals copying everything on the right-hand side. And then finally, to solve for t, we divide both sides by negative b. So we get t equals all of this ln divided by negative b. I think that's good. And then in that space there, I'm just going to use my inverse notation. So what was the name? This was an f of t function. And so this is f inverse of p right here. So interpreting this, if you give this function a value of p, it will output the corresponding value of t. So let's make sure we can say those in words. Oh, well, there actually isn't. It's just a population growth. So I guess P is population and T is time. So if you give this function a certain population, plug in the value of P there and there, then this entire function will output how long it will take to get to that specified population.